Here are a couple problems to practice and illustrate the difference between making calculations of average power and instantaneous power. The first problem involves a calculation of instantaneous power. We're told that there's a car with a 160 horsepower engine, travels with a top speed of 110 miles per hour, and we need to determine how much is the net resistive force acting on the car. Now, the first two questions are just unit conversions. So we know the power is equal to 160 horsepower, and we're told that the car is traveling with a velocity of 110 miles per hour. So we need to convert the horsepower into watts and the speed into meters per second. So let's do part A first and convert the power into watts. So we'll say 160 horsepower over 1, and then we need to convert and change from horsepower into watts. Well, there are 746 watts for every 1 horsepower. So this is just a matter of multiplying the numbers together. We get about 1.19 times 10 to the 5th watts. If we want to change the speed from miles per hour to meters per second, then we need to do a proper unit conversion. Let's see, I know if I run 4 laps that I've gone 1 mile, and for every lap that I run, I go 400 meters. So laps cancel, miles cancel, and now we're left with meters per hour. So we need to get rid of hours now. I'd like to change that into seconds. There's 60 minutes in an hour and 60 seconds in a minute, so we can just say there's 3,600 seconds in 1 hour. So, right, hours have canceled out. We're left with meters per second. So we're really taking 110, multiplying by 4, multiplying by 400, and dividing by 3,600. So we find that the speed is equal to 48.9 meters per second. And you might have learned a shortcut in the past. It says take the value in miles per hour, divide it by 2. So let's see, 110 divided by 2 would give us 55, and then subtract 10% from that value. So 55 minus 5.5 would have given us 49.5. That's not too far off from the more exact value of 48.9. So dividing by 2 and taking off 10% gives a decent approximation, but it'll always work out to do a correct unit conversion. So really the guts of this question are in part C to find the resistive force. So instantaneous power is the vector dot product of force with velocity. And that means we just need to rearrange a little bit here. Force, and in this case, the force and the velocity are parallel to one another. So we can just say it's the magnitude of the force times the magnitude of the velocity. So the force is nothing more than the instantaneous power divided by the top speed, 1.19 times 10 to the 5th watts divided by 48.9 meters per second. But keep in mind that a watt is the same thing as a joule per second. So the seconds cancel out. Now we're left with joules per meter. But a joule is a Newton meter. So a Newton meter divided by a meter just leaves us with newtons, and that works out nicely since we're trying to calculate a force. If you grab a calculator and divide 1.19 times 10 to the 5th by 48.9, you get a force of about 2,430 newtons. Okay, the second problem has to do with average power. So here we're told that there's a 1/2 horsepower garage door opener, and it takes 11 seconds for the garage door to open up. We're also told that it costs 25 cents for 1 kilowatt hour of energy. Now let's write that out. 1 kilowatt hour is 25 cents. you might just hear kilowatts. That would be a mistake. Kilowatts are a unit of power. Make sure you're paying attention to these units. A kilowatt hour. What you're really doing is multiplying some amount of power times some amount of time, which is really a calculation of energy. In fact, a kilowatt hour is equal to 3.6 million joules of energy. Okay. In the end, we're asked, what would it cost to open and close the garage door 20 times a day, given these values? And we can assume that the energy required to open and the energy required to close are one and the same. So what we really want to do here is find out how much energy does it take just to open the garage door. If we multiply that value times 2, then that's the energy it takes to open and close. And if we multiply that times 20, then this would give us the amount of energy per day. Okay, so let's see. How do we figure out how much energy it takes to open? Well, if average power is equal to change in energy divided by the corresponding time, then the change in energy is nothing more than the average power multiplied by the time. So the energy it takes to open the garage door is equal to, let's see, we have to do another unit conversion, don't we? 1/2 of a horsepower would be the same thing as, well, we just need to divide 746 by 2. So we can say a 1/2 horsepower garage door opener is a 373 watt garage door opener. And that's a common value. Most garage door openers are sold as either 1/2 horsepower or 3/4 horsepower, depending on the weight of the door that they have to open. So 373 joules per second multiplied by 11 seconds means the energy it takes to open the garage door one time is equal to 4,103 joules. So if we apply this formula, the energy for an entire day is 40 times that value, right? 20 times 2. And so that comes out to 1.64 times 10 to the 5th joules. And so in the end, we just need to convert this to a cost. Well, we have the conversion factor. 3.6 times 10 to the 6th joules would cost 25 cents. So we can take 1.64 times 10 to the 5th joules. And if we want to get rid of joules and change it to cents, it's 25 cents for 3.6 times 10 to the 6 joules. So joules will cancel out and we'll be left with a final monetary value for this operation. So this comes out being equal to about 1.14 cents. Oh, pretty cheap, right? Yep. Energy from the utility companies is provided at an absolute steal. It's a bargain. And because of it, we're not readily discouraged from tapping in to the energy that's provided, and we end up maybe being wasteful. I don't recommend going through your garage door 20 times a day. Probably an excessive use of the available cheap, easy, harnessable energy that we'd rather conserve in its mechanical form. Thanks for watching.